Friday Science at St. Andrews. And today, what's becoming a tradition, at least one time during the semester, we ask a distinguished person to come and just talk. We'll have a conversation, and we'll see where that goes. The next one, I believe, is Dr. Matt Clark, who's going to talk about job finding and things, or maybe something else. He wants to talk about radio waves and things, but I don't understand any of that, so I don't know. At any rate, it's my pleasure to introduce Dr. Alan Dotson. And in just a second, I'm going to sit down and we're going to have a conversation. And depending on, you've seen some of these before, and depending on how it goes, if you might have a question to ask, you certainly can. But for right now, we'll just get started and chat a little bit. Recognize Doug Calhoun as a distinguished alumnus and videographer and all of that. So when he's all ready, we'll begin. Questions, you ready?
I'm good.
All right. Well, Dr. Dotson, welcome to Friday Science at St. Andrews. And just by way of introduction and getting into my first question, you graduated from Wake Forest and then you went to UNC Chapel Hill. And your bachelor's degree was in physics?
Yes, sir.
And your PhD was in physics?
Yes, sir.
And then you went to Western Michigan University for 17 years, and then you came to St. Andrews, and you told me 1981.
Correct. Good memory.
So, I just made that up. It was a good piece of luck. So, talk a little bit about where did you grow up?
I grew up over in Stanley County, North Carolina. It's about 75 miles west of here. And I tell my physics students that if there was not such a thing as hydroelectric energy, hydroelectric power, I would not exist. Dayton is the name of my little town where I grew up. Had a one horse in those days. It was a one horse town, and the horse was Alcoa Aluminum Company, had a smelting plant there. And my father had graduated from Wake Forest and taught a little bit, but he had become the chief chemist there at the Alcoa plant. He was in charge of making sure that the metal was pure enough and so forth. And anyway, he is the proud owner of my family, of course, because my mother was teaching in the Dayton schools at that point, and they had a clubhouse where they would house both the new people. The plant was very new, and so they would house the new people and the school teachers in different wings of this clubhouse. And that's where they met, and that's why I'm here. That's why I exist. So, hydroelectric power, which is what the plant runs on, basically, because it's right on the Yadkin River, and you get some good hydroelectric power there. So that's the reason for my existence. And after that, it was all physics.
So it sounds like your family had a scientific education background. What led you to physics as opposed to maybe chemistry or English or something?
Well, actually, it was not all physics after that, because I was first more interested in biology. I was interested in insects, and my father let me have one of the powerful microscopes that they used at that time to inspect the aluminum. They got a better model, and so he gave that microscope to me. And I started looking at protozoa, and I would have been a protozoologist if I had stayed in that field, because I love protozoa as well as insects. But my father had a little telescope, and essentially he got me interested in looking at stars, and I was interested enough to subscribe to an astronomy magazine, popular magazine called Sky and Telescope. And they ran a series of articles on these cosmic rays that come in from outer space. They're still sort of mysterious even today as to where exactly they're coming from and why they're coming. But anyway, these are little particles, elementary particles. And so that got me interested in particle physics. And that just led to a career in physics. So there it was.
So what led you to Wake Forest?
Well, probably because my father went there and my older brother was there too.
Okay. So, right now, these are mostly questions about how did you end up where. So how did you end up in Western Michigan?
I decided that I wanted to see some other part of the country when I finished at Carolina. And so I interviewed at several schools across the country, not to the west, but in the middle part of the country. And I particularly wanted to go to the Midwest if possible. And so I got this invitation to come and interview at Western Michigan. And the first thing I asked about how it was in the wintertime, and the fellow who was interviewing me said, "Well, do you like snow?" And I did like snow, and I still do in small quantities, smaller than you get in Kalamazoo, Michigan. But anyway, that was the offer that I accepted.
And while you were there, you just taught physics, or did you do anything else? Were you active in faculty senate work and governance, anything like that?
Not particularly. I was the department chairman for a while, and so I had some idea as to what you're going through. But I didn't do a whole lot of work in that area. I was mostly focused on just physics. So it's what I liked.
And if I remember right, 3 or 4 years ago, you went back, rode the train back to work with colleagues for a while on the Higgs boson. Can you describe that?
Right. You want me to describe the Higgs boson?
No. I want you to describe the continuing relationship with your colleagues.
Well, we always exchanged Christmas cards and that sort of thing, kept up with each other through the years. And so, actually, I'd gone back about that was my third time back, I think. So, the other times I'd flown back. But it was good to keep up with them. And now we're getting too old to travel. We still do Christmas cards.
So when you went and met with these colleagues, did you just sit around and talk about the old days, or did you write mathematics on the blackboard and argue about things, or
well,
what?
We didn't sit around and reminisce much, but I was interested in what had been going on in Kalamazoo, you know, as a city, which I lived in for so long, and they kept me up to date on that and so forth. And we did talk a lot about the physics.
Yeah, well, what I'm probing about is, what do physics people talk about when they talk about physics?
Right. When they are talking about physics?
Sure. Well, did somebody just write something on the board and y'all discussed it or argued about it, or
well,
You said a bunch of physics
We
words?
were
or what?
going through a book, a popularization that dealt with the Higgs boson.
Mm-hmm.
And so we would go like one chapter at a time, you know, through the book, and basically just talk about what it all boiled down to.
Mhm.
So that was just to make sure.
It sounds highly stimulating.
It was very stimulating.
Okay, so I'm trying to follow chronology.
Mhm.
What brought you to St. Andrews?
Well, it was January.
So did it have something to do with snow?
It had something to do, once again, with snow, right? Because I'd been there for enough years that I knew that I was never going to really take up skiing or sledding or whatever, and I needed to get back to the south. And so, and particularly, I wanted to get back because my father had died and my mother was getting up in years and needed somebody to live with her. And so I arranged for her to come down and live with me here in Orangeburg when I got back.
So why in particular did you choose St. Andrews?
Because that's really awful.
So,
Right.
well, I remember when Mr. Kaufman sat here and talked about his experience, that's kind of a standard question now, is why St. Andrews? He saw a picture on the wall.
Oh, yeah.
So you just looked and that's where
I
the,
saw an ad. It said
Okay.
needing a physicist and several other faculty members at the same time, which was unusual.
Mhm.
I guess we're maybe in that same situation right now here. But anyway, one of them was a physics person, and so I decided, well, check it out. So I took a train then down from Kalamazoo to Chicago, Chicago to Philadelphia, and Philadelphia down to. So, enjoyed it.
and so what did you find when you got here?
I found.
In other words, what was St. Andrews in 1981, January?
It was, well, actually, I didn't come until March, and they housed me over in Pate Hall for a night. And I woke up in the morning and a mockingbird was singing, and I said, "Oh man, I hope they offer me a job here." But anyway, I had bunches of interviews, you know, the usual routine, and so they decided to offer me a job, and I certainly wanted to accept. It's interesting that just before I got the job offer, I decided that it had been quite a while. They had been talking with other folks, I'm sure, about the job. And I decided, well, I guess I'm just going to be a Kalamazooan for the rest of my life. And then in a day or two, I got the phone call saying, we want you to come down for an interview.
Mhm.
So I didn't become a Kalamazooan for life after all.
Well, let's shift gears a little bit. We've got you traced all the way to here. In my time here, which I haven't been here very long.
John, Michael lets you say that.
That's an inside joke that I tried saying I was a new person for, this is the 9th year saying new person. And I'm not the new person anymore,
Not quite.
not biology anyway. So one of the things that's noteworthy is the way you conduct your classes. For example, you got a new physics book, so you worked all the physics problems. Or started working on them until.
I found the physics problems I could work.
Oh. Well, you just looked at them and said,
No,
oh, I
you
can
try
work
them
that
out.
one.
You try them out now. But seriously, I did want, of course, to assign homework problems to people that I was sure, knew how to work.
Mhm.
That's embarrassing, when that does not happen.
And so is that a typical way of doing things, or is that just your way of doing it?
I think it's pretty standard. if you're gonna explain something to a class, you better be sure that you can explain it correctly.
Yeah. Well, that makes sense. What's the hardest thing that you struggle with learning and doing? A particular area, physics or something else?
Well, physics labs have always been a challenge for me because I was purely a theoretician, not an experimentalist when I was going through my training. It would have probably rounded me out better to get a master's along the way, which I did not. I just went for the PhD. And if I had stopped and gotten a master's that had something to do with experimental physics, that would have given me a little more expertise in that area. But coming down here, there had been physics courses offered, of course. I came when the college as it was then was 20 years old. The classes opened in 61 and I came in 81. And so obviously they had fitted physics before, but they hadn't had a physics professor for a while. And so there was physics lab material there, and I started putting together some labs that I understood how to do, and I carried with me some of the labs that we had at Western Michigan, some of the descriptions, that is, not the equipment, but the descriptions. And so they had similar equipment here, and otherwise I would order some, and so forth. So that was a big challenge in terms of getting started in the physics area here.
So let's go down a path of following this experiment and building labs. The reason I want to follow this is that one year, and it was read at the last Science Homecoming Research Exposition, you wrote a poem to Mr. Cobb.
I did, yes.
So would you talk a little bit about the relationship of setting labs up and having a director of logistics? Did that help or hurt or?
The fall that I came in 81 was when Rooney was just about to take a sabbatical of some sort to do, what was it you were going to do that year?
Well, I spent the fall term up at the UNC with the chemistry department technicians working on servicing equipment. How to fix it.
How to fix equipment. Right, and an important task for a laboratory chairperson. But anyway, I was feeling really good about my labs until I heard that Rooney was going to not be there that semester. But we made it through. But I've always depended on Rooney to get me out of whatever binds I was in. And by the way, Rooney, I've got a little piece of equipment that broke, and I'm going to get you to see if you can fix it. But he's Mr. Fix It and Mr. Explain It, and Mr. Correct my unwise ideas about certain experiments. So it's been a really good working relationship for me through the years.
And you taught, when did you first teach astronomy? Or have you always taught it along since you've been here, or was that a new?
When I came, we had what's called the January term, where everybody the students took one course and only one course for the month, and the professor would just teach one course. And the first course I taught was on the Dancing Wu-Li Masters, which was a popularization of modern physics and some of the same problems that still affect quantum theory, for example, which I'll talk about a little bit later. But then the second time, I wanted to vary it a little bit from one year to the next. And the second time, I decided I would do astronomy. which was kind of bold because I'd never had an astronomy course, but I studied it for a long time when I was younger, and made it through all right. So.
Well, I seem to remember that, and you can correct my memory, that we and still have a fairly good-sized Meade telescope. And if I remember right, we sent it off, got it repaired, it came back, needed to be repaired some more, got it back. And that you and Mr. Kaufman could not find the moon with it. Could you?
This is true.
Could you explain?
Well, we could have.
It was a full moon,
Yes,
I think.
it was, or pretty full anyway. But that was the least of our worries. The fellow who was really an astronomer on our physics and science staff was teaching computer science, Bill Rowland. And he has been up in the mountains now for about 5 years or so in retirement. But he was active in computer science, but he had actually sponsored some real research at his previous school up at King College on the boundary between Virginia and Tennessee over there. He and a fellow professor who also came here had built a telescope up there and an observatory to hold it and so forth. And so he was the one who basically said what telescope we should get, and it was always somewhat of a issue, even with him, to get all the right instructions right. It's a very complicated system that they had at that time anyway. And Rooney and I have tried to get those corrections down pat so that we can use it reliably. But in Bill Rowland's absence, we have not been able to do that. So,
But you did end up with a coordinate so that the thing would find the moon eventually. Or not. I'm giving away.
We would have trouble with the initialization of what you do, and that would lead, of course, to you tell it to just go to the moon, and it won't go. It'll go to somewhere where it thinks it's the moon, but it's not the moon. So it doesn't work suitably. We need Bill Rowland to come back and explain to us what to do.
Well, it seems simple to me, but I guess not. If it won't point in the right direction, you can't find the moon even though you can see it.
That's right.
So you've also been involved not just in physics and working problems, not just astronomy, but you've looked wider and even written a book.
Yes.
And so would you talk about that a little bit, the wideness of your experience?
In 1967-68, I took a sabbatical, I guess you'd call it, from Western Michigan, and went out to Iowa State University in Ames, Iowa, and worked with some particle physicists out there. And it was a very enjoyable operation. One of the things that I did was I would be going to church there down the road and in walking distance from where I was living there on campus, and got into a Sunday school class with this gentleman who was, I'm not sure he was a preacher, but he had done a lot of work with helping out problems, helping solve problems in the Chicago area, which was a pretty dangerous area there that he was working. And so he was representative of the church doing that. And one time he was talking about his operation there and said basically they were going through this neighborhood, and it's a neighborhood where you don't stop. And he had asked the driver, he was new to it, he had asked the driver, well, what if you have a flat tire? And the driver says, you just go on the rims. And I thought to myself, wow, there's more to church activity than just singing and all that stuff, praying and so forth. And I started getting more interested in the church. I was raised as a Baptist and would go to church. I faithfully went to church, but to me it was just sort of like, something that you needed to do, and I kept it up doing it. But when I got back to Kalamazoo, I decided to take a more active role in the church. And I did that and taught Sunday school there, and also got interested in theology. And finally I decided I would go to seminary for a year and learn some more about the connections between science and religion. I was still interested in science, of course, but also I'd gotten interested in theology, and so I wanted to look at the connections between the two. And that led to my rather extensive introduction to theology, because I spent a year there and took a lot of theology-based courses and so forth. And so finally, when I came here, I again started teaching in Sunday school and so forth, but I decided I wanted to express my beliefs, to see, for one thing, whether they wanted to throw me out of the church or not, because I was an American Baptist up north, and an American Baptist is more liberal, typically, than a Southern Baptist. And so I was, in fact, Martin Luther King was an American Baptist. But I came back quite liberalized, you might say, and I wanted to just say what I believed. And so this book was basically sort of my witness in terms of, number one, that religion is about something real, and number two, basically it's something that's important for us all to have. So that's why I wrote the book.
What's your favorite thing to read? Or group of things to read?
Well, I do more reading, I guess, in theology now than I do in physics, because, in fact, they say that old physicists tend to become philosophers. And basically, philosophy as related to science becomes sort of where I am as well. So I read a good bit of books. In fact, we have a study group over at at Scotia Village of people, about 4 or 5 of us get together and we go through books that are not just pure theology, but applied theology to the world situation. That's the sort of thing I like to read about.
So let's change slightly. Listening to you at the beginning, I understand where the word paramecia
You know
came
Paramecia.
from.
Right.
So you had an interest early on.
Looking at through the microscope there, my favorite protozoan was Stylonychia or Stylonychia or something like that, which has little feet on it. Does that mean feet or something like that?
I don't know.
But anyway,
I don't work with things
Don't
you can't see without a microscope.
but anyway, I saw Paramecia and so forth. I shared a bedroom with my older brother, and he was off at Wake Forest at that time. And I would bring in these quart jars of pond water or lake water, and they would sit there with a little vegetation in there, you know, to help them have something to eat. And I would use a microscope on them. After a week or two, the aroma of that water brought some comments of unfavorable nature from my brother. He said, "Do we have to have this stinking water in here?" So, but anyway, that was really an important part of my life at that point.
So we know that part. The title is Paramecia and Paradoxes.
Right, right.
Would you lead us through the other half of that?
Yes.
What's Paramecia got to do with paradoxes?
Well,
Or not?
it's really not a connection between them, except I'm the connection, in the sense that I was interested in Paramecia, and incidentally, along about that same time that I was interested in Paramecia and Styloneipia, I also was a big fan of pickled pig's feet.
Oh, that's where that came
That's
from.
where that came from. So,
I was going to bring that up.
yeah, I thought maybe you would. But anyway, I recently did some extra work for a former student to help her get rid of an incomplete. And she, at the end, she had heard that I was a fan of pickled pig's feet, and so she gave me a nice big jar of pickled pig's feet. Well, I'm not a fan of pork much anymore. I'll eat a hot dog maybe twice a year, but pickled pig's feet, they found a happy home, but it was not with me.
It perished in the flood, I hate to tell you.
Oh.
It did.
No, I gave the pickled pig's feet away.
I thought you gave it to me.
No.
Oh, that's a different pickled pig's feet. You had another benefactor.
Oh, yeah, right.
To explain this a little bit more fully, Dr. Dotson is very nice about asking people how they're doing, how are things going, what are you reading now? Very interested in people. And at some point, it was not a good day. And came by and asked me how I was doing, and I said, well, it's a kind of a day that makes you want to listen to country music, drink long neck beers, and eat pickled pig's feet.
Oh.
Sort of, well, it was that kind of day. I don't know what the curative potential is there. But unexpectedly, Alan told me, says, well, I love pickled pig's feet. And I had trouble putting that all together, physics and pickled pig's feet. In fact, the original title for this was Quantum Mechanics and Pickled Pig's Feet. So this was not some random occurrence. This does have a continuum. So what about paradoxes?
Well, I'm glad you asked. The paradoxes in modern physics and quantum physics are primarily based on the fact that our physical properties, our fundamental properties like space and time and velocity and so forth, our concepts don't work well down at the quantum realm. In fact, you can say that Heisenberg's uncertainty principle was one of the early paradoxes, which says that in what I think is the proper form, and a lot of this is really controversial, other people would disagree with what I'm about to say, but anyway, the Heisenberg uncertainty principle says that you cannot measure an atomic sized particle, like an atom or whatever, or anything below that, subatomic. You cannot measure the momentum and the energy or the velocity and the position. These are sort of canonical variables. You can't measure, let's talk about position and velocity. You can't measure the position and the velocity of a particle at the same time. And basically, the reason for that is that the qualities of these two properties just don't allow it down at the atomic realm. Heisenberg was a famous physicist, German physicist, and there was a joke that was shared among physicists at that time that Heisenberg was traveling too fast down the highway, and he was pulled over by a highway patrolman, and the patrolman said, "Do you know how fast you are going?" And Heisenberg said, "No, but I know exactly where I am." In other words, you can't squeeze down position and philosophy together at the same time, because it just doesn't work at the quantum level. It works beautifully at our level. We can just take pictures and so forth and figure out what the velocity is exactly and the position. But it's not just, in other words, it's not dealing with just our measurement capabilities. It's dealing with the nature of those properties. And another paradox is called entangled states. You can have two photons, the quanta of light, or you could have two electrons, for example, that are put into a state where what one measures determines what the other one measures. In other words, if we talk about the spin of particles, which is not exactly like the physical spin of this can here, but it's reminiscent to it because of the way it works. And you talk about it, if the spin of one electron is up and it's entangled with another one in a spin zero state, then the other one has to be down, like so. And that's true regardless of how far away they are. If they are entangled, then this one up means one down just automatically, so to speak. So you can take one of them on a trip to Mars somewhere, let's say, and the other one here, and neither one of them's been measured yet for spin. And if this one is measured again for spin up, then this one automatically is spin down immediately. Well, now how can that be? Because the speed of light is just 186,000 miles a second, and Mars is a whole lot farther away than 186,000 miles, and that would be a second. But they've done this on short distances. Of course, they haven't taken their equipment to Mars yet, but they've verified it in terms of short distances, like several meters, for example. And basically, it's instantaneous because that's the nature of being entangled. And so, how does the one know what the other one was, and therefore know to come back in the other direction? And it's a matter of spin is one of these quantities here that does not work at the submicroscopic level, the atomic level, and below that. It just doesn't work. And the other one that I wanted to present is delayed choice experiments. If you look up delayed choice experiments on the internet and go to Wikipedia, I want to read to you what it says about a photon that's traveling in an experiment which has another photon. It's like these two electrons with the spin, for example. They can entangle the what is it? The orientation of the photon. You can entangle two of them. And in some situations, you can get one of them entangled with the other, and basically you can do an experiment on one of them, and that again will determine the outcome on the experiment of the other, but it's involving a delayed choice. Now, let me read to you what the first sentence or so is in Wikipedia on delayed choice experiments, and then I'll talk a little bit about the experiment and then read it again, and I think it'll make more sense to you. If a photon in flight is interpreted as being in a so-called superposition of states, that is, if it is interpreted as something that has the potentiality to manifest itself as a particle or as a wave, but during the time of flight is neither, then there is no time paradox. This is the standard view, and recent experiments have supported it. And going back to one of my heroes, Niels Bohr, we must take into account the complete experiment. That's how you really look at that. And here's the story. You have a photon which is entangled with another photon, like with two electrons. And so the question is, what kind of a pattern does it make when it goes through a double slit or when it goes through a single slit? If it goes through a single slit, you just get one distribution pattern like the normal distribution. But if it goes through two slits, and basically, in other words, acts like a wave and goes through two slits, then what happens is that you get stripes. You get a striated pattern corresponding to what you can do just with ordinary life under ordinary circumstances. Well, if Bob takes the wave option in his with his photon, and the other one over here, usually called Alice, A and B, and Alice goes ahead and lets the photon land, then basically what happens is that if Bob hits the wave option, then the pattern in which this particular photon appears is the interference pattern. But if he hits the particle configuration, then the overall pattern makes it look like it was just going through one slit rather than two slits. So basically what's going to happen here is that it will be determined that it's either in part of the wave pattern or in part of the particle pattern. Basically, the problem is, in terms of the reality of it, you can use the other one to determine that after the first particle lands. In other words, the first particle lands, and then you can decide whether it's part of a wave or part of a particle type pattern. If a photon in flight is interpreted as being in a so-called superposition of states, that is, if it is interpreted as something that has the potentiality to manifest itself as a particle or as a wave, but during the time of flight is neither a particle nor a wave, then there is no time paradox. This is the standard view, and recent experiments have supported it. So basically what it's saying is that, again, in this case it was the nature of the pattern that you're going to get. That doesn't work like you would think it would work, because the particle, when it lands, will be in one pattern. If after it lands, you can do this other particle after it lands. And after it lands, you can determine whether it's going to be a particle or a wave. So that's kind of strange. That's a paradox.
So we have time for one more question, a comment.
All right.
Like, what advice would you give to students sitting in the room? Work hard, be well, be happy, or what?
Find what turns you on, makes you really interested, makes you not want to stop thinking about it, and just follow your dream. That's what I do.
And with that, we'll say thank you very much.
You're very welcome.